Hey everyone, welcome back to our Tech Talk. Today we're diving into a topic that's super critical for power systems but often flies under the radar: isolation transmitters. I'm joined by my colleague who's been working on these for years. Let's start with the basics. Why do we need isolation transmitters instead of regular ones?
Great question. In power systems, you've got all these complex grounding systems, massive EMI, and connections between different voltage domains. A regular transmitter just can't handle that. The key here is triple point isolation separating input, output, and power supply from each other. This breaks ground loops, suppresses common mode interference, and keeps both people and equipment safe.
Right? And the installation specs are impressive too. I saw that they have at least 3.0 kVRMs dielectric withstand between each port for 60 seconds. That's reinforced insulation levels and CMRR over 100 decibels. That means it can ignore noise that's common to both input lines.
Exactly. And let's not forget EMC immunity. They meet IEC 6100004 Level 4 standards. That's the highest level for industrial environments. We're talking plus or minus 8 kilovolts contact ESD, 4 kilovolts common mode surges. These things can handle just about anything a power substation can throw at them.
So how does the digital architecture contribute to accuracy and stability? I know they use 24-bit sigma delta ADCs.
Oh, that's where the magic happens. The microcontroller runs this continuous loop: sample, compensate, diagnose. They do temperature gain and offset compensation down to 30 to 50 ppm per degree Celsius. That means even if the temperature changes, the readings stay accurate. They also do nonlinearity correction and synchronous window RMS for power signals, which is crucial for getting precise voltage and current measurements.
And for temperature sensors like PT100.
They have 3-wire lead compensation and cold junction compensation for thermocouples. Plus, the onboard reference does self-checks to maintain stability, less than 0.05% FS per year. That's long-term reliability you can count on.
Let's talk about real-world applications. First up, generator terminal measurements. What does that entail?
So for generators, you need to measure all the electrical parameters: voltage, current, frequency, power factor, you name it. The SET503C1P2A2102 model is perfect for this. It takes inputs from PT and CT secondaries, processes them, and communicates via IEC 61850 or IEC 608705104. Having unified, accurate inputs really improves a GC and a VR performance.
And transformer temperature monitoring? That's critical for preventing overheating.
Exactly. The SET500A1Y21 is often used here. It accepts PT100 inputs with Callander Van Dusen linearization. It gives local HMI 2 alarm stages, 4 to 20 MA retransmission, and overload management. Super important for extending asset life.
What about station DC systems and PV strings?
For station DC-like control buses, batteries, chargers, you need to monitor 0 to 300 VDC. The same goes for PV strings up to 1500 VDC. Isolation transmitters here help with DC health monitoring and finding PV anomalies quickly. They can be deployed centrally or distributed depending on the setup.
And SF gas compartments. That's another key area for substations.
Right, SF is used in GIS and GCBs, so monitoring pressure, density, and moisture is essential. The transmitters convert dew point to PTMV and provide alarm and lockout functions. This keeps those high-voltage compartments safe and reliable.
Let's touch on power supply and communication. What options are available?
The auxiliary power is really flexible: 88300 VDC or 85264 VAC. That covers all standard substation voltages: 110, 125, 220 VDC, and 220 VAC. For communication, they support all the major protocols: IEC 608705104, Modbus, TCP, RTU. And they have security features like RBAC, allow lists, and signed firmware.
When selecting an isolation transmitter, what should engineers look for?
Start with the measured quantities, ranges, CT-PT ratios, max voltage. Then check isolation specs. Make sure it's at least 3.0 kVRMs. EMC Level 4 is a must for harsh environments. Don't forget power supply compatibility and communication protocols, and accuracy chain, ADC resolution, compensation algorithms, self-calibration plans. Oh, and mechanical factors like mounting and IP rating.
Any common pitfalls to avoid?
Definitely. One big one is cable shield termination. You have to terminate on the correct domain, no cross-domain bonding. For PV systems, make sure the input impedance is high enough for voltage dividers and check leakage power. Also, confirm 4 to 20 MEDA compliance voltage and load. You don't want signal loss there.
And these aren't just for power systems, right? They're used in other industries too.
Exactly. Process DCS, oil and gas with intrinsic safety barriers, metals and mining to mitigate ground loops from VFDs, rail and marine for DC systems, new energy storage for BESS monitoring. They're really versatile.
So, wrapping up, why are isolation transmitters so important?
They're the signal safety boundary and data quality anchor. With triple port isolation, level 4 EMC, algorithmic compensation, and standard protocols, they turn noisy, complex measurements into stable, reliable data. This supports safe, economical operation throughout the asset lifecycle. They're not just components, they're the guardians of power system reliability.
Well said. If anyone wants to learn more, they can visit Odis Electric's website or contact Tony Zhang. Thanks for joining me today.
My pleasure. Hope this was helpful for all the power engineers out there.